Hi, in this lesson, we will learn the product rule and the quotient rule, and those rules will be used to find the derivative of a function when the original function is a product or two functions are being multiplied, or if there are two functions that are being divided, so a quotient. So, product rule first. If we are taking the derivative of a product of two functions that we'll call f of x and g of x, then the derivative would be the first function f times the derivative of the second function, g prime, plus the second function, g, times the derivative of the first function. Both addition and multiplication are commutative, so these two can be switched up in order, as well as these two can be switched up in order. Or you could put the second expression first and the first expression second. So when you memorize this, just remember that when you are combining them, you're taking the original function times the derivative of the other function, and then the other function times the derivative of the first one. So here's an example. We are calling our function f of s, and our two products are 5s squared plus 2 or 2s squared minus 1 for g. So this will be f and this will be g in our formula above. So I need f prime and g prime, so I've written them here. F prime is 10s. That's the derivative of f. And g prime is 4s. That's the derivative of g. And so now we will put it together in our formula. So I'm using this formula. So I have f times g prime plus g times f prime. And then from there, we want to do a little bit of algebra to simplify this. So I distributed the 4s across, and I distributed the 10s across, giving us this third line right here of 20s cubed plus 8s plus 20s cubed minus 10s. And then if we combine like terms, we will get that our derivative is 40s cubed minus 2s. This derivative could also have been found without using the product rule, but in order to avoid using product rule, we would have had to expand this first or FOIL out those expressions. So if I multiply these two binomials and then take the derivative, when you FOIL, you would get 10s to the fourth minus s squared minus 2. That's still your f function, your original function, and then the derivative would be 40s cubed minus 2s, same answer that we got by using the product rule. Okay, so here's an example of where you have to use product rule. So it won't help if you distribute, you wouldn't avoid using the product rule. My two expressions are e to the x, that's your f in the product rule formula, and then 3x squared minus 5 would be g. So the derivative of f is f prime, and that's e to the x, and the derivative of g would be 6x. So when we put this together, we have to apply this to product rule. So I did f g prime, that's on this line, plus f prime g, and that's the second part. So if you look at this product and this is a product, and in order to simplify, I can see that they have something in common, which is e to the x. So I'm going to factor out an e to the x, so that goes in front. And then what I'm left with is three terms, and I put them in order. 3x squared plus 6x minus 5. And you're done. That is your derivative. Okay, so let's move on. Let's evaluate a derivative at 8. So let's evaluate f prime of 8 for this function, which is again a product. I have a product of a cube root times a linear function. So the third root of t is my f, and I'm rewriting that as an exponential so that I could take the derivative easily. So that's equal to t to the 1/3. And my g is the second piece, so that's 3t plus 1. I wrote f prime below, that's 1/3 t to the negative 2/3, so I've applied power rule to that. And then the derivative of g prime is just 3. So when I put this together, plugging into the product rule formula, I have f g prime, that's this piece, plus g f prime, that's this piece right here. Okay, so can't just leave it like that. So all I did was I plugged into the product rule formula, but I need to make this look a little bit better. So I rewrote all of my exponentials as radicals. That's an optional step. And I corrected for this negative exponent. So I have 3 times the cube root of t plus 3t plus 1 over 3 times the cube root of t squared. So at this point, it won't really help to get a common denominator or anything, because what I need to do is evaluate it at 8. So I'm going to plug in 8 for t. So everywhere there's a t, you see an 8 now. So the cube root of 8 is 2, but when you multiply it by 3, you get a value of 6. Here, the cube root of 8 is 2. This time I square it, so that's 4. Multiply that by 3. That gives me 12 in the denominator. My numerator is 25. And then in order to add 6 and 25 over 12, I do need a common denominator. So the 6 gets multiplied by 12, numerator and denominator. So it got multiplied by 12 over 12. So that gives us 72 over 12 plus 25 over 12. And so my value is 97 over 12. All right. So let's learn more about the quotient rule. We use quotient rule when we are taking the derivative of a quotient of two functions. So I have f of x divided by g of x. G of x is in the denominator. So your rule is as follows. It is your denominator function times the derivative of the numerator function minus the numerator function times the derivative of the denominator function, all divided by the function in the denominator raised to the second power. Here, order is important. Subtraction is not commutative. So although you can do f prime g minus g prime f, so multiplication is still commutative, but this product here has to go second, and this one has to go first. So order is important here. Okay. So we want to find the derivative by using the formula. So remember, formulas replace the definition of the derivative. Definition of the derivative would certainly take quite a bit of work to do algebraically, so these rules are much more convenient. So my numerator is what I'm calling f, so that's 33x. My denominator is g, that's 4x to the 5th minus 3x minus 4. F prime is 33. G prime is 20x to the 4th minus 3. So I just have to now plug in these values for f prime, g, and g prime into the formula. So I have g f prime minus f g prime all over g to the second power. Okay, so we need to do our simplifying in the numerator. Leave the denominator alone. It is not going to help you to expand this. So leave that as that polynomial raised to the second power. But in the numerator, I need to distribute the 33, and I have to distribute the negative 33x to the second binomial. So that gives us this line here. But I do have like terms, so I end up, so these 99x's cancel. So I end up with 132x to the 5th minus 660x to the 4th minus 132 over the polynomial squared. So this one does factor. You can factor out a 132, leaving me with this polynomial times 132. Nothing cancels, but it is a good idea to always factor if you can, because sometimes you can cancel with something in the denominator. In this case, you cannot, so this is your final answer. All right, so let's use quotient rule again. This time, the function I am interested in taking the derivative of is x squared minus 1 over e to the x, and then I'm going to evaluate it at 0. So my numerator is f, my denominator is g. So f prime is 2x, g prime is e to the x. So remember, the formula is gf prime, so here's gf prime minus f g prime all over g squared. So it's e to the x to the second power. All right, so similar to one I did before with e to the x, these two products in the numerator have a common factor of e to the x. So I factor that out. And that leaves me with 2x minus x squared plus 1, because I distributed that minus sign across, over, and when I square e to the x, I get e to the 2x. But that just means that this e to the x will cancel with 1 here. So I no longer have e to the x in the numerator. And my denominator is just e to the x in the next line. And I can factor out a negative from the numerator. So I end up with negative parentheses x squared minus 2x minus 1 over e to the x. So now I'm going to evaluate it at 0. So plug in 0 everywhere that there's an x in your problem. So you end up with a negative 1 over, and this one is just 1. So that's 1 over 1, which is a derivative value of 1. Okay. So here we're going to come up with a formula. So we're going to use the quotient rule to derive a formula for the derivative of 1 over v to the x. So notice that my numerator is just a constant. It's not, it doesn't have a variable in it. But I'm going to apply quotient rule to this quotient of 1 over v to the x to come up with a formula for its derivative. Okay, so in this example, using the formula, f would be 1, the numerator, and g would be v of x. And because we know that the derivative of a constant is 0, f prime is 0, and g prime, well, we don't know what v is, but we know that it's the derivative of v. Okay, so that's exactly what I plug into the formula. I did gf prime minus f v prime over v of x squared. Okay, so the first term cancels because of the 0. So I am left with a negative v prime of x over v of x squared. So that is the derived formula when you have a numerator that is 1 and my denominator is some function v. Okay, no need to memorize that. You can easily figure that out just by using quotient rule. Okay, so we've talked a lot about tangent lines, and now we're going to talk about normal lines. So a line that is normal to a curve means that it is perpendicular to a curve. And remember that lines that are perpendicular to each other have slopes that are negative reciprocals of each other. Therefore, a tangent line to a curve and a normal line at the same point would be perpendicular lines. So we know that a tangent line has a slope that's equal to the derivative of the curve. And now we know that that slope will have a slope that is a negative reciprocal of the slope of the normal line. So what are negative reciprocals? Examples would be 2/5 and -5/2. So the signs are opposite. One is positive, this one's positive, the other one is negative, and the numerator and denominator flip. If it's something like 7, the negative reciprocal would be negative 1/7. But if the original number is negative, then it turns to a positive, and the reciprocal of 1/5 would just be 5. So that's just a few examples of negative reciprocals. Okay, so for example, if I have one line that is 3x plus 1 and the other one that is y equal to negative 1/3 x minus 4, we would consider these lines to be perpendicular, and in fact they would intersect at a 90-degree angle if you were to graph them, because the first one has a slope of 3, the second one has a slope of negative 1/3. 3 and negative 1/3 are negative reciprocals of each other. Okay, so let's bring in this concept along with what we've learned so far about calculus. So the question is, do the curves of y equal x squared and y equal 1/x² intersect or cross at right angles? So at any point, would those two curves, if they were to be sketched, would they ever intersect at right angles? All right, so what that means is that they are going to meet at some point. So we would want to figure out when do they share the same point, which means we have to set them equal to each other. So when is x squared equal to 1/x²? If you multiply both sides of the equation by x squared, you would get that x to the 4th equals 1. And when you take the 4th root of this equation, you would get that x is equal to plus or minus 1. That means that these two curves are going to intersect at right angles at -1 and at +1. And to know what the actual points are, you would plug in +1 and -1 into either this or this, and you would find that the points of intersection are -1, 1 and 1, 1. Okay, so to find out whether they intersect at right angles, we now have to use the concept of the derivative and evaluate them at these points of intersection. And if the slopes are negative reciprocals of each other, then the answer would be true. If they are not, the answer would be no. They intersect, but not at right angles. Okay, so let's take the derivative of the first one first. So the derivative of x squared is 2x. So when x is -1, my derivative is -2. When x is 1, my derivative is 2. Okay, so far I know that at x squared I have one slope that is -2 and another slope that is 2 on the parabola. So now we need to take the derivative of 1/x². All right, so I decided to use quotient rule for this, although it can be done another way, which I showed you here below. So if we use quotient rule, this is g f prime minus f g prime over g squared. So x squared squared is x to the 4th. But then this x in the numerator cancels with one of these. So my derivative is -2/x³. When I plug in -1, I get that the derivative is 2. And when I plug in +1, the derivative is -2. So we can conclude that although they do intersect, they do not intersect at right angles, because at -1, this one has a derivative of -2, but the second function has a derivative of +2. Although they are opposite in sign, they are not reciprocals of each other. And the same thing happens at 1. X squared has a slope of 2. 1/x² has a slope of -2. These are opposite in sign, but they are not reciprocals. Okay, so they need to be reciprocals of each other. All right, so here we're going to use the concept of normal lines to find an equation. So we want to find the equation of the line that is normal to the curve y equal to 1/2 x to the 4th plus 1 with a slope of 4. Okay, so remember, normal means perpendicular, and we know this normal line has a slope of 4. Okay, so we are missing a point, and in order to find the point where this is going to happen, I need to use my derivative. So I know that my derivative, the relationship between y prime and my curve is that it's the slope of the tangent line. So the negative reciprocal of 4 is -1/4. So that's what I should be setting my derivative equal to in order to solve for a point. So my derivative is 2x cubed. The derivative of y, this y, is 2x cubed. If I set that equal to the slope of the tangent line, I get this second line here, the equation 2x cubed equals -1/4. Divide both sides by 2, or multiply by 1/2, I'll get that x cubed is -1/8. Take the cube root of both sides, and the cube root of -1/8 is -1/2. So I get an answer of -1/2 for x. But now I have to find my y value. I plug in -1/2 into your function, which was this one. So I get 1/2 times -1/2 to the 4th power plus 1. And when you work that out, you get that y is 33/32. So now that means that when I'm finding the equation of the normal line, I'm using the slope of 4, which was given, and the point -1/2, 33/32, which we just found. So I put that in the point slope formula. Y minus 33/32 equals 4 times x minus -1/2 becomes a plus. I distribute the 4x and I add the 32, and I'm here. If I get a common denominator for 4/2 and 33/32, I multiply this one by 16, and that gives me a final answer of 4x plus 97/32. All right, so this next one is similar. Find the equation of the line that is normal to this curve. Y equals 8 minus x cubed, but this time I've given you a point, -1, +9. So similar to the last one, I'm going to use the concept of the derivative in order to help me find the slope in this case. So I know that the slope of the tangent line is the derivative, and the derivative of this is -3x squared. If I figure out what that slope is at -1, plug that in, I'll get that the slope of the tangent line is -3. So therefore, the slope of the normal line is the negative reciprocal of -3, which is +1/3. So now that I know that my slope for my normal line is +1/3, I can use 1/3 and the point that was originally given, -1/9, in order to find the equation. So I'm left with y minus 9 equals 1/3 times x minus -1. That gives me, when I distribute, I'll get 1/3 x plus 1/3. Then I have to add 9, but 9 has to get combined with 1/3, so I wrote it as 27/3. That's equal to 9. And then you can add your fractions, and so you're left with y equal to 1/3 x plus 28/3. So that's it for this lesson. Give the homework a try.